Salutations, population of planet Earth, and welcome to Miscellaneous Chemical Reactions, where I perform miscellaneous chemical reactions for your benefit, education, entertainment, and enjoyment. Today, I will be performing 4 chemical reactions. First, I need to utilize the magical power of video editing to don appropriate laboratory attire. The first reaction I have set up is the classic vinegar and baking soda combination. Shown here is the balanced chemical equation. Sodium bicarbonate, or sodium hydrogen carbonate as it is sometimes called, also known as baking soda, reacts with acetic acid in vinegar to produce carbon dioxide, water, sodium ion, and acetate. Now let's see the reaction in action. Here, I have 1/3 of a cup of baking soda and 1/3 of a cup of vinegar. I am going to mix the two, and we will watch what happens. As you can see, carbon dioxide gas bubbles are formed, along with water, sodium, and acetate. Let's bend the space-time continuum and use the magical power of video editing to warp to our next reaction. Here is a propane-powered grill. Unfortunately, I don't have any New York strips to cook, but the combustion of propane happens to be our next chemical reaction. Here is the balanced chemical equation for the combustion of propane. Propane, when exposed to sufficient heat, combusts with oxygen to produce carbon dioxide and water. Now, let's see the reaction in action. Remember to always exercise extreme caution around open flames. Voila! Fire! Here we have a water electrolysis machine designed by yours truly. When electrical current from this 9-volt battery is applied to the water molecules separate into hydrogen and oxygen. These containers here trap the gases. Hydrogen gas will be produced by the negative cathode on this side, and oxygen gas will be produced by the positive anode on this side. Here is the balanced equation for the decomposition of water. When electricity is applied to water, it separates into hydrogen and oxygen. This equation shows that there will be twice as much hydrogen as there is oxygen. And we will be able to prove this. After encountering slight technical difficulties with the last water electrolysis machine, I designed the new water electrolysis machine 2.0 complete with Lego. This new machine holds all the components in place so you can watch without my hands getting in the way. As you can see, hydrogen gas bubbles are forming off of this electrode and getting captured up here. Partway through the electrolysis, you can now notice the gas bubbles traveling up through the tube and gathering up at the top. We'll be able to see more of this later on. On the right side, you can see lots of hydrogen gathered at the top. On the left, you can see a very small bubble of oxygen gas. New interesting development. Oxygen produced in previous experiments has formed rust on this left thumbtack, slowing the further production of oxygen. Ultimately, the experiment was mixed success, as most of the oxygen has been expended, deteriorating the left tack instead of collecting in the tube like it was expected. The main reaction of water electrolysis has still occurred, yet there is also a secondary reaction with this tack rusting. The results from the experiment proved our equation in showing that there should be twice as much hydrogen as oxygen formed. Water electrolysis is often used as a cheap method for producing hydrogen and oxygen gases for sale. Let's go outside for our next reaction. I think I'll do this one without our magic video editing power. I think I'll need this for our next reaction. Our next reaction is... there was a new crowbar too. When exposed to oxygen, my iron crowbar oxidized, or rusted, as it is more commonly called. Here is the balanced equation for the formation of iron oxide. Iron plus oxygen yields iron oxide. In this case, iron 3 oxide. Well, I guess we can't do what I had planned for our last reaction, but this crowbar incident makes up for it. Here is another example of rust found on the left brass pin that was used in the water electrolysis reaction. The left pin was the anode and was where the oxygen was formed during the electrolysis. That is why it is the only pin that is oxidized. Thanks for joining us here on Miscellaneous Chemical Reactions. Tune in eventually, same random time, same YouTube channel.